Hi, welcome to our continuing discussion over calculus and vectors. Now, yesterday we looked at the derivatives of vectors. Today we're going to take a look at the antiderivatives, or the integrals of vectors. And very similar to what we did yesterday, where we have a function. Remember, we have the x component, the y component, and the z component of a vector. We're going to look at each part individually. So just like yesterday, we are going to work each component independently from each other. So, for example, if the integral of r of t is, we will look at as the integral of f of t, that's the x part, the integral of g of t, the y component, the integral of z component, or h of t, and don't forget when you're going to always have that plus c to it. And again, you can write it in chevron notation, or you can write this in component notation. It's up to you which one you would prefer to do. I do sometimes find it easier to write these in the component form versus the chevron form, but we'll see. I mean, I'll try it either way. So now in the first example, we're given r prime of t is given as cosine of ti minus 2 sine tj plus 1 over 1 plus t squared k. So we have our x, our y, and our z components. And this satisfies our initial condition. Now, pretty much any time, you might remember this from Calc 1, anytime they say the initial condition, we are going to have to solve for the c's. Okay, don't forget those constants of integration there. And given the initial condition, r of 0, at r of 0, my x value is 3. That's what it says. Minus 2j, so I got my y component, plus k, and there's my z component. Remember what this is really kind of saying right here is that r of 0, that x of 0 equals 3, y of 0 is negative 2, and z of 0 is 1. We want to find the antiderivative. So we're going to integrate this. So if this is r prime of t, to get r of t, you can use, like I said, you can use component form, or you can write it in chevron form. Either way is acceptable. It's up to you. So let's go ahead and do the chevron form. I want the antiderivative of cosine 2t, don't forget the dt, you need that there, comma, the integral of negative 2 sine t, don't forget your dt, comma, and then my integral of 1 over 1 plus t squared dt. Alright, so we have to integrate. Now you might remember this is a u substitution, so now we're going to integrate. So this is first one's a u substitution, u is 2t, and you might recall last year we talked about a way to shortcut this is when we get our du is 2 dt, so we're just going to divide our answer by 2. So when we integrate this one, we are going to get, well, the antiderivative of cosine is sine of 2t. We just multiply it by 1/2 because of our u. So we get 1/2 sine 2t plus c1. Just like yesterday, last year, don't forget your constant of integration. We'll talk about these later on. Comma, the antiderivative of negative 2 sine. Well, the antiderivative of sine is negative cosine, so this becomes 2 cosine t plus, and again, I'm going to call this c2 because I don't want to confuse it with this constant right there, so we call that c2. And over here, oh no, you might not remember this one. This has been a while for us. This is our arctangent. Okay, recall the rule. You're going to see this one quite a bit this year. The antiderivative of 1 over x squared plus 1 dx is the arctan of x plus c. So this is going to become the arctangent of just t. Arctangent of t plus, and again, we're going to call this c3. Now again, you could write this in chevron form, and you can look at my old notes right here. That's exactly what I did. I wrote them in component form, I, j, and k, and that's okay as well. Sometimes I just prefer chevron form. I guess the old geometry person me, but I know a lot of physics students prefer the I, j, k. Either one's acceptable. So we have to find c now. So for the first one, this is my x component. These are my x's, these are my y's, and these are my z's. So I can use my initial condition to solve them. So we are given that x of 0, remember, is 3. So I can set this, the whole equation, to 3. So we would get 1/2 sine 0 plus c1 equals 3. Well, that's easy. Sine of 0 is 0, so c1 is 3. So r of t, my first component, would just be 1/2 sine 2t. Looking at the next one, cosine, these are my y, so we were told that y of 0 is -2. That's right up here. It's hard to see there. It's -2. So if I plug this in, we would get 2 cosine 0 equals -2. Whoops, plus c2 equals -2. There we go. Cosine of 0 we know is 1. So this is saying we subtract it, and we subtract that 2, we get c2 is -4. So our y component for our function is going to be 2 cosine t minus 4. And then we look at our z component. We're told z of 0 is 1. So we know that the arc tangent of 0 plus c3 is 1. Well, the arc tangent of 0 is just 0, so we get c2 is 1. Remember, where is tangent equal to 0? Is at 0 radians. So our equation for the z's would just be the arc tangent of t. And there is our original function right there. There is the function right there. Whoops, plus 1. There we go. Got my plus 1. There. Need that plus 1 there. Don't forget that. Alright, so let's go and take a look at another example. So again, that's kind of a mess up right there. Again, so that should be an r prime. So they're telling r prime of t is equal to cosine of t minus 1, 2t plus 3, and the natural log of t. Ah, boy. We know this one, right? That is our integration by parts. That's our parts right there. So we'll see that today. So when we integrate this, we are looking at the antiderivative of, whoops, so it's easier to write it this way. The integral of cosine t minus 1, the integral dt, don't forget your dt, the integral of 2t plus 3 dt, and the integral of the natural log of t dt. Of course, there's another way we could write this as well, and I'll show you that maybe later on. When we integrate the first one, the antiderivative cosine, we already know is sine, so this becomes just sine of t minus 1 plus c1. And let's see here, the next one, this would be, what's that going to become? That's just t squared plus 3t plus c2. And over here, you got your integration by parts. So if we let u would have to be the natural log of t, dv would be dt, so du would be 1 over t, and v would be t. So this becomes, what's that? Remember the rule, uv minus the antiderivative of v du. So we're going to multiply those together. So we get t, natural log of t, minus the antiderivative of v. Oops, don't forget that was t right there. So we would get 1 over t times t dt, which those cancel. And we're left with t, natural log of t, minus, that just becomes t, plus c, in this case c3. So we would get t, natural log of t, plus c3. And there would be our integral right there. Now, another way we could do this one, and I'm going to go ahead and show you this real quickly. There's another way we can do this one right here. And this is perfectly acceptable too. I could write my integral this way instead. Just one big integral, and I would get cosine t minus 1, 2t plus 3, natural log of t dt. Do it like this, a little bit shorter, and so your antiderivative then would be, of course, sine t minus 1, t squared plus 3t. Notice the only difference is I'm not putting my plus c's in yet. And this is, of course, when we did our integration by parts, t natural log of t plus t, and at the very end, plus c. You can write it this way as well. Sometimes a little bit quicker, just depends on what you're trying to do with it. Okay? All right. All right, so for the last one, now we are going to evaluate this integral, okay? Now, one more thing I want to kind of mention. Now, this is kind of a big thing. You see the c right here? The c in all of these, c right here, the c1 is a constant in the x direction. Here, this is the constant in the y direction. This c3, that's our constant in the z direction. So when we come to here, it is important to remember that this constant right here, this is a vector. This has an I, a j, and a k component. So C could be a vector. It's going to be a vector I, j, and k. It's going to have those type of components right there. And that's going to be very important for us later on. For example, remember our first example up here? We could have written this as the following. 1/2 sine 2t, 2 cosine t, arctangent of t, plus my components, 0, -4, 1. So that's another way we could have written that. So you're going to see a lot of these different ways throughout the next few months. All right, the last one. Now we want to evaluate. So we want to evaluate the integral from 3 to 5. So again, this is our fundamental theorem of calculus. And once again, we're going to treat each part independently from each other. So we don't need the plus c's because this is FTC, because they're all just going to cancel. If you forgot about that, look at my videos from calculus, first semester calculus. So we're going to evaluate the first one. I'm just going to do the component part. This is our sine of t minus 1. That's going to be evaluated from 3 to 5. T squared plus 3t. Again, evaluate that from 3 to 5. And t natural log of t minus t. Again, evaluate that from 3 to 5. And that's not too bad to do for the first one. We're going to get sine 4 minus sine 2. Plug in 2 here. We're going to get, that's 25 plus 15, so that's 40, minus 9 plus 9, so that's minus 18. This is just our fundamental theorem, right? F of 5 minus f of 3, f of 5 minus f of 3. And over here, this is not so fun. We're going to get, I'm going to use this, 5, natural log of 5 minus 5, minus 3, natural log of 3, put that in brackets, minus 3. And again, you got f of 5 minus f of 3. And there's our fundamental theorem of calculus right there. All right, hope you guys enjoyed the video. I will see you all later. Bye-bye.